Like, when is the midterm? Haven't set the date yet, so I'm thinking maybe it's time to start thinking about that, like when we want to have the midterm. Well, none of us wants to have a midterm, right? Including me, but it's just going to be in class, right? So, you know, it's not an evening test that you have to plan around. And I want it to be roughly halfway through the semester, maybe, you know. And spring break this year is later than usual because of the slightly kludgy new academic calendar. It starts on the weekend of March 29th, Saturday, March 29th. So I'm thinking possibly like the Tuesday of that week leading up to spring break. Is that like a massive prelim week for people? Because most courses have like 2 prelims and they're like 1/3 and 2/3. And I'm thinking if I put mine a half, it'll be kind of displaced from. Okay, you're nodding. Yes. Anybody else? Like, suppose we had it say, what would it be? Tuesday, the 25th of March. It's not the Ides of March. It's not St. Patrick's Day. It's not spring break. It's none of the above. Yes? March the 26th. Okay. That's not too awful a hardship, I don't think. If you have plenty of advance notice, you know. I'm thinking maybe that day. I think it's unwise usually to put it the last class before or the first class after spring break. So, all right, I'm not hearing any big objections, so I'll think about that. I'll think about that and I'll get back to you. Okay. All right, so one more pass. Any other questions about anything before we move on? Okay. Well, today I think today and Thursday we're going to be able to wrap up the general discussion of Markov chains and then move on to how we're going to use these things. So, still talking about these Markov chains. And we have all this notation, and I'm not going to put it all up again. And I just want to remind you, at the very end of class last time, I introduced the following notation. So, given 2 states of a Markov chain, and I always, whenever I say Markov chain, of course, I mean a Markov chain in discrete time with a countable state space or a finite state space and transition probabilities that are homogeneous. They don't depend on time. So it's the same context we've been talking about the whole time. So given 2 states I and j, and this is our notation for the state space, we say that I goes to j. That's the way I pronounce that little thing when Rij is bigger than 0. Remember what Rij is? Rij is the probability that given you start in state I, you reach state j in finite time. Okay? So that's what it means for I to go to j. And this is not the same as saying P of Ij is bigger than 0. This says that there's an arrow between states I and j with a non-zero label on it in the transition diagram. All this means is that maybe you can't get it to it in 1 step, but you can get to it in, say, 17 steps or 59 steps. There's a positive probability that you can get from state I to state j in finite time. And at the very, very end of class last time, I put this fact on the board. And by the way, we're going to be going through a bunch of facts and theorems about limits and everything. I'm not going to prove these things in class. I'm going to give you pieces of arguments for some of them, but I can refer you to the handout for all the detailed proofs, if you wish. And some of them require a certain level of masochism to sit through, you know, but some of them are easier than others. So anyway, here's the fact. In this context, if I is recurrent and I goes to j, then j is also recurrent moreover, j also goes to I, and in fact, not only is Rij bigger than 0 and Rji bigger than 0, they're both equal to 1. Okay? So that's an important fact about recurrent states. That if you have a recurrent state I and there's some other state you can reach from it in finite time with positive probability, then you know automatically, first off, that state is recurrent. Second off, you can get back to I from that state with positive probability in finite time. And in fact, with probability 1, you will get from I to j in finite time and from j to I in finite time if you run the Markov chain. Okay, now here's an example of a situation where I'm going to give you a quick argument for part of this, but not give you the entire proof. Okay. So suppose I is recurrent and you can reach j from I in a finite number of time steps. Why, for example, is rji positive? So here's sort of a sketch of part of the proof. So say I is recurrent and I goes to j. Why is it true that rji is positive? So we know right away that rji is bigger than 0. Now, why is that true? I is recurrent, which means that with probability 1, I get back to I in finite time given that I started there. There's no way to go through the Markov chain starting from I and never get back to I, at least no positive probability way. What if rji weren't positive? What would that mean? That would mean that once I hit j, I have 0 probability of getting back to I in finite time, right? And that contradicts recurrence of I, because say I start in I, all I have to do to never come back to I is go to j in that case. Boom. So we know right away that rji is bigger than 0, and in fact, that rji equals 1. Because if rji were not equal to 1, then what I could do starting from I is first go to j, and then go off on some path that never comes back to I, which would be the case, would be positive probability of doing that if rji were not equal to 1. Okay? So else we could start in I and go to j and then follow a path, a positive probability path. And I'm being a little loose here because a single path is generally not going to have positive probability, but you can have a positive probability family of paths that never returns to I, contradicting the recurrence of state I. That is to say, rii equals 1. That's the same thing as I being recurrent. And that's all I'm going to give you of this proof. You can do this kind of reasoning a lot of the time about Markov chains without ever writing down any formulas or equations or inequalities. But to finish this up, to dot all the i's and cross all the t's, show that j is recurrent, et cetera, et cetera, et cetera, show that rij is equal to 1, what you have to do is mess around with equations. And I'm not going to do that. And it is in the handout. And that's one of the non-masochistic proofs. No suffering required to understand it. Okay, everybody get this? Everybody get this kind of logic here? Okay. All right, so now here's some terminology. Here's a definition. Say I'm given a state I in S that's recurrent. I want to define the recurrence class of state I to be the set of all j in the state space S that you can reach with positive probability in finite time from I. That is to say, the set of all j's such that I goes to j. That's what the recurrence class of a state I is. Now, by this fact, all the states in S, in the recurrence class of I, so I'm going to use C sub I to be that. C sub I equals the recurrence class of I. Note that for all j in C sub I, we have Rij equals Rji equals 1, and also j is recurrent. So the recurrence class of any state consists solely of recurrent states, and all of those states are such that you can reach them in finite time from I with probability 1, and you can reach I from them in finite time with probability 1. So this is like a tight little family of states associated with I. All right. Now here's an interesting thing. Here's another fact. And I thought about numbering these facts, fact 1, fact 2, and all that, but I'm not going to do that. Given two states I and j, two recurrent states I and j, so given two recurrent states, and by the way, am I going too low on the board for folks in the back? Are you able to stretch up and see? Okay. Given two recurrent states I and j, if I look at their two recurrence classes, either the recurrence class of I and the recurrence class of j are disjoint, or they're equal. Yes? C sub I is the recurrence class of state I. That's class. I suppose I could use K sub I. If we were teaching in German, it would be Klasse. And in French, it would be C, because it would be Classe, you know, C-L-A-S-S-E. Yeah, Olympic train of thought makes you think of all these foreign languages and whatever, you know. But C in Russian would be S, so we would have to use K or X, maybe Class. Any Russian speakers in the audience? No? Okay. All right. So if I'm given any two recurrent states I and j, their recurrence classes are either disjoint or they're the same. So to see this, all I have to do, let's suppose they're not disjoint. So suppose Ci intersects Cj is not equal to the empty set. All I have to do is show they're the same. So I'm going to let K be some state that's in that intersection. So what does that mean? That means K is reachable from I and K is reachable from J. By the earlier fact, K also goes to I and also goes to J. And moreover, the probability of reaching I from K is 1. Probability of reaching J from K is 1. But we don't even care. And thus, what is going to be true? Because I goes to K and K goes to J, that's going to imply that I goes to J, which means that J is in C sub I, right? And also J goes to K and K goes to I implies that J goes to I, which means that I is in C sub J. Which means that because J is in C sub I, and I goes to j and all that kind of thing, everything in C sub j is in C sub I, and everything in C sub I is in C sub j. Because j is in C sub I, that means that Cj is contained in C sub I, and this implies that Ci is contained in C sub j, which means that they're equal. And that exhausts the possibilities. Either they're disjoint or they're equal. They can't intersect in a sort of a non-trivial way. Now, as a result of this, we now have another sort of splitting up of the state space of the Markov chain. Okay, so thus, if you look at the Markov chain, we can refine our splitting of the state space into transient states union recurrent states. And this, of course, is a disjoint union because the state can't be both transient and recurrent, into a splitting that has the transient states as one piece and then S sub r split up into a whole bunch of mutually disjoint recurrence classes. So S equals ST union, the disjoint union, and I'm not going to try to notate this, of all the recurrence classes. So you have your transient states, you have a bunch of recurrence classes, all of them are mutually disjoint, and that exhausts the state space. Okay. Recurrence classes are examples of a more general concept, and that is the concept of a closed set of states. So here's some terminology. And what do I want to use for a set of states? A set, let's call it capital A, of states is closed. What does that mean? What does that mean? It means that given that you start in I, you can't get to any, or start in A, you can't get to anything that's outside of A. So it's closed if and only if for all I in A, I does not go to K for any K that's not in A. So you start in I, or start in A, implies you stay in A with probability 1 for all time. Okay, so A is kind of like Vegas, right? In a sense. Right? Does that make sense? I don't know. I guess, yeah, all right. So anyway, that's what it means for a set of states to be closed. Now notice that every recurrence class is a closed set of states. So observe. Actually, let me be even more general. The whole state space is obviously, trivially, a closed set of states. So S itself is a closed set of states. Okay. And every recurrence class is also a closed set of states. If you start in a recurrence class, you can't leave it, because if you start in a recurrence class and you go to some other state, that state is still going to be in that recurrence class because you can reach it from whatever the guy was whose recurrence class that is. Okay, so those are examples of closed sets of states. Now, what's the most trivial example you can think of a non-empty closed set of states in a Markov chain? One state with a probability 1 arrow to it. Okay, that's a good point. That's what I was looking for. So here's some more terminology. If J is in the state space S and the set consisting of just the state J is closed, we call J an absorbing state of the Markov chain. Now, what does it mean for the set consisting of J to be closed? What that means is that there's zero probability of ever getting to any other state in finite time starting from J. And what that means is, in the transition diagram for this Markov chain, you're going to have this. J is going to be there, and there's going to be a probability 1 arrow coming back to J, no matter what other arrows are coming into J. So with maybe some entering arrows, but no other departures. So that's kind of like an individual hotel in Vegas. Right. I won't push that one any farther. Don't worry. All right. So that's an absorbing state. Anyway, now if you think about it, you'll see that if you look at a closed set of states, it's kind of like a closed set of states is the state space of a kind of like a private little Markov chain that just happens in there. So any closed set of states is the state space of a sort of a private little Markov chain that sort of happens in there. Okay. And in particular, if, say, A is closed, we have, because P of I comma K is equal to 0 for all K not in A, the sum over all states J in A of P of I comma J equals 1 for all I's. Okay. So taking the transition probabilities for the big old Markov chain and just restricting them to this set A gives us a set of transition probabilities for this private little Markov chain whose state space is A. So thus, the Pij, quote unquote, restricted to A gives us the transition probabilities for the private Markov chain whose state space is A. Okay, so now we're getting sort of a picture of what's going on globally in the Markov chain. We have these transient states, and we have these recurrent states, and among the recurrent states, You can divide those up into disjoint recurrence classes. Each of those recurrence classes is a closed set of states. If you start in there, you stay in there. And questions arise as to, like, say I start in a transient state, do I end up in a recurrence class? That kind of thing. So we're going to start addressing those kind of questions now that we have a grip on the global structure. And in order to do that, we're going to have to refine the definition of recurrent states. It turns out there's different flavors of recurrent states, 2 different flavors of recurrent states. Okay, so here's one more concept we're going to need. Suppose I have a state that's recurrent. Remember this thing we defined 2 times ago and also last time. So recall that Tj, capital Tj, is the first positive time the first n bigger than 0 such that the state at time n is equal to j. And recurrence is the same as saying that the probability that starting from j, Tj is less than infinity is equal to 1. And remember what this is. This is f. This is the sum of all, this is r sub jj, which is the sum over all k from 1 to infinity of f superscript k sub jj, using our other notation. That's what it means for a state to be recurrent. Now we can compute, we know that the probability starting from j that Tj is less than infinity is equal to 1, but what is the expected value of that? We computed that for an example last time. Okay, so consider computing Ej of Tj. Remember, what's that? That's the expected value of Tj given that you start the Markov chain in state j at time 0. That's going to be the sum from k equals 1 to infinity k f superscript k sub jj. Now, just a reminder, we've computed this for an example. Squeaky eraser. I think switch this one so you can. Yes. So recall that for this example, where we had 1 minus p here, p 1 minus q, q, we found that E2 of T2 is equal to P plus Q over P, and E1 of T1 equals P plus Q over Q. And we made some sense of that by saying that, what if P is really small relative to Q? Well, that means that the expected time it takes to get back to state 2, given that you started in state 2, is really big. Why should that be the case when P is really small relative to Q? Well, it's reasonably likely that you go from 2 to 1. That's probability Q, but very unlikely that you get back. Okay, so we discovered those last time. Now, the thing here that's key to notice is we were able to compute these things just by running through geometric series reasoning and all that sort of thing. But it's possible that this sum here does not converge. It's possible that Ej of Tj is infinity. Okay, so here we had Ej of Tj less than infinity for all states. In general, that might not be the case. It's possible in a Markov chain to have the expected value of Tj, given that you started at state j, equal to infinity. And that might seem counterintuitive. You know with probability 1 you'll get back to j in finite time, given that you start in j. But if the tail of that fkjj thing is too thick, then that sum defining ej of tj might not converge. So intuitively this happens when f superscript k sub jj doesn't decay fast enough as k goes to infinity. It has to decay because they all have to sum to 1. But it might not decay fast enough. Saying it doesn't decay fast enough is saying that with high probability you might have to wait a really long time to get back to j, given that you started in j. And that's why the expected time you have to wait might be infinite. Now this is indeed an anomalous occurrence, which is not to say that it's a zero possibility occurrence. So we have to take it into account. So here's the terminology. This is the additional concept I'm talking about here. Terminology. If j is recurrent, we say that j is positively recurrent if and only if this thing that I'm going to call mj, which is ej of tj, is less than infinity. We say that j is null recurrent if and only if that thing ej tj equals infinity. Now, obviously, mj, that ej of tj is always strictly positive. It can never be 0 because you're taking an average value of a bunch of strictly positive numbers. But it can be infinite. And that's what it means for a state to be null recurrent. And as it happens, null recurrent states are somewhat anomalous. And generally, we're going to be in a situation where we assume that there are none of them, or we see that we can pretty much wish them away because of various limit theorems. So note, null recurrent states are somewhat anomalous. And in fact, as we'll see, when you have a finite number of states in your Markov chain, you can't have any null recurrent states. It's not possible. So in fact, they never show up. They never happen when S is finite. But later on, we'll see how they come in. In that example up there, the PQ example, both of those states are positively recurrent, as you can see, because this M1, which is E1 of T1, is P plus Q over Q. That's positive, less than infinity. And I'm assuming, of course, as usual, that P and Q are both positive and less than 1 in this example. OK, so here's another fact. Now that we've got this notion of null recurrent states and positively recurrent states, that if you look in a Markov chain and you look at a recurrence class, it turns out that in a given recurrence class, all the states are either going to be positively recurrent or all the states are going to be null recurrent. So if C in a state space is a recurrence class, then either of the following two options holds, nothing in between. All states in C are positively recurrent, XOR all states in C are null recurrent. And therefore, when you read about Markov chains, people talk about positively recurrent classes or null recurrent classes. What they mean is recurrence classes, all of whose states are, respectively, positively recurrent or null recurrent. All right, so I think we're done introducing these big general concepts, and now we can start talking about some of the big limit theorems for Markov chains. And this is where the rubber meets the road for applications, as we'll see. Does all this make reasonable sense? Yeah, Drew.
I'm just trying to come up with examples in my head of what could be null recurrent states. Would it infinite random instead of null recurrent?
It depends on the probabilities. If you look in the handout, which clearly you haven't, actually it's worth noting this down, that there are Markov chains, all of whose states are transient. There are Markov chains, all of whose states are null recurrent. And in the handout, I give this example. Matt, I can't see his face when you're doing that. Okay. I give this example where you have this chain that has a bunch of states in a line, and you go out to the next one with some probability, and each one can possibly return to the first state and no other. And depending on what the numbers are on those branches, either all those guys are positively recurrent, or all those guys are transient, or all those guys are null recurrent. So have a look at that, and yeah. Okay, so back to the original question. Does this all make reasonable sense so far? All right. Okay, so now it's time to talk about some of the big limit theorems for Markov chains. Okay, so now, so the first couple of, and these are very important all caps limit theorems for Markov chains. And the first couple of limit theorems I want to talk about address the following question. What fraction of the time does the Markov chain spend in each of its states over the long haul? So roughly speaking, they address the following question. Here's the general question. What fraction of the time over the long haul, and over the long haul is sort of like a euphemism for as n goes to infinity, right? Does the Markov chain spend in each of its states? And of course, there's lots of things upon which the answer to this question depends, and even phrasing it mathematically takes some delicacy. So what we're going to do, we're going to look at two situations here. One of them is about the expected value of the fraction of the time it spends in various states, and the other one is a stronger assertion about probability 1 that it spends this fraction of time over the long haul in the given states. So that's the general question. And to answer this question, I want to introduce yet another piece of notation. Sorry, okay? So more notation. One more. That's all we need for now. We're going to have some more a little later on in the class. So one more piece of notation. If I'm given a state J, in S, I'm going to let n sub j, this is another random quantity associated with the Markov chain, n sub j of little n, capital N sub j of little n equal the number of times that the Markov chain hits state j during the time interval 1 less than or equal to m less than or equal to little n. So that's the number of hits of j up through time n, not counting n equals 0, that the Markov chain hits state j. So roughly speaking, whenever I use this particular shirt and I go to hang it up at night, there's always all this white stuff on the left sleeve, and I can never remember why. And then when I teach the next class wearing this shirt and I have to roll the left sleeve up repeatedly, I remember why. And then by that night, I've forgotten why again. So, you know, maybe I'll send myself an email after class. Don't forget that it's because you have to roll up the left sleeve. And why I don't have to roll up the right sleeve, I don't know. Maybe it's because I played tennis for many years and my right forearm is bigger than my left one. I don't know. And I'm boring all you people watching at home. So, anyway, thus, for any n, if I look at nj of n over n, that's the fraction of the time that the chain spends in state j over the interval 1 less than or equal to little m less than or equal to n. Okay? And what we're going to be interested in is the behavior of that quantity over the long haul. That is to say, as little n goes to infinity. And first we're going to look at its behavior, the expected behavior over the long haul. Then we're going to look at the probability 1 behavior. So here's the first limit there. And it's going to have two parts here. In this context, if j is any state, then the limit as little n goes to infinity of ej of nj divided by nj of n divided by little n is equal to 0 if j is transient or null recurrent, and it's equal to 1 over mj if j is positively recurrent. And again, mj here is equal to ej of tj, the expected value of the time, the first time that you get back to state j, given that you started in state j. That's one piece. And the other piece is a slight refinement of that. If I is any state, then the limit as little n goes to infinity of ei of nj divided by n. Now that was ej. That's given that you started in state j. This turns out to be, again, 0 if j is transient or null recurrent. And it turns out to be rij divided by mj if j is positively recurrent. Now, just a hand-wavy thing of why why we expect this second part to be true given that the first part is true. If I start in any old state I, two things can happen. I get to j in finite time, or I don't. Right? If I never get to j, starting from I, then nj, probability sub I of nj equals anything positive is going to be 0, so I'm going to end up 0. So that's why this rij appears here. Why does the 1 over mj appear there? Well, given the first thing there, once I get to state j, I'm going to spend a fraction 1 over mj over the long haul in state j. So if I get to state j from I with probability rij, then that's why I have rij over mj. But why does the first thing make sense? Let me just give you the intuition. And this is a masochistic proof that if you want to read this one, definitely, take an Advil about halfway through. No opioids, that you won't be able to understand it. Okay, so here's the intuition for this ej of nj of n divided by n converging to 1 over mj. And I'm just going to draw a picture here. Okay? So say you start in state j at time 0. So this is time 0. And then you do stuff, and then you come back to state j. First time. Then you do stuff, and then you come back to j second time. And so on and so on. Now, how long does it take to get back to j the first time? Well, the expected value of that is going to be mj, right? So the expected value is mj of how long it takes you to get back to j the first time. Now, once you get back to j that first time, everything resets. The Markov property resets everything. And so now the question of when do you get back to j the second time is the same as the question of how long did it take to get there the first time starting at 0. And so again, this length of time is mj expected. And j the third time, again, you're going to have mj expected. And so on, right? So you expect to wait about mj time steps between successive appearances of j. So let me write that down. So between successive visits to state j, you expect to wait mj. So what is that? How long does it take to get L visits to state j? Again, the chalk sleeve. So you expect to take, over the long haul, time, say, LMJ to make L visits to J. Right? And therefore, let's call that N. So L over N is going to be like L over LMJ, which is like 1 over MJ. That's the intuition behind that. And qualitative statements that you can make, the bigger TJ expected value is, the smaller the fraction of the time you're going to end up spending in state J. So here's some qualitative assertions. So EJ of TJ, which is our MJ, big corresponds with you spend a relatively small fraction of the time in state J So you spend, given that you started in J, a relatively small fraction of the time revisiting J. And if it's small, the same thing. You spend a relatively big fraction of the time revisiting J, given that you started in J. Okay? If you have to wait a long time to get back, you don't come back very often over the long haul. Let's go back to our PQ example. And then we'll take the 3-minute break before the second limit theorem. So back to this one. We had M1 equal to P plus Q over Q. M2 equals P plus Q over P. So what we have to do to figure out the average amount of time you're going to spend in state 1, because R11 and R12 and R21 equals 1, we have the following, that the limit as n goes to infinity of E1 of n2 divided by n2 of n, I should say, that's the same as the limit as n goes to infinity of E2 of n2 of n divided by n. By this theorem, using both of the pieces together, that's going to equal 1 over m2, which is P over P plus Q. And the same thing for E1 of n1 of n over n. That's the same as the limit of E2 of n1 of n over n. And keeping the subscript straight is a task. That's 1 over m1, which is Q over P plus Q. So what does this say? That means that if P and Q, remember we've been repeatedly asking the question, what if P is very small relative to Q? So thus, if P is much less than Q, what is this telling us? It's telling us that we're spending a relatively small fraction of the time over the long haul in state 2 versus the fraction of the time we spend in state 1. So we spend way less a fraction of the time in state 2 than we spend in state 1 over the long haul. At least in terms of expected values. So expected value-wise. And that's what we expect. Yeah?
Sorry, is that E1 N2 then E2 N2?
Yeah, E1 of N2 of N, E2. That 2 is kind of ugly, eh? There. Thanks. Matt?
When you have the first slide, you go from like E1 N2 to get equal to E2 N2.
Yeah.
Can you explain why that's true?
That is, this really is generally going to be R12 over M2 from the second part of our fact. But R12 is 1.
No, I'm just asking, so like the probability, the expected value that you start in 1 and N2 is equal to the probability you start in 2 and N2. Is that just because you're going through?
No, it's not probability, it's expected value. The expected fraction of the time you spend in state 2, given that you started in state 1, over the long haul is the same as the expected fraction of the time you spend in state 2, given you started in state 2 over the long haul, and it's equal to 1 over m2.
Right there, like, why are those two things equivalent? Like,
Okay, well, here, put 2 and 2 here,
Okay.
right? And then over here, put 1 and 2, and use the fact that this R12 is equal to 1.
Okay.
Got it?
Yeah.
Good question. But the point I'm trying to make here is from the intuition about this Markov chain, if P is way less than Q, if it's hard to get from 1 to 2 versus getting from 2 to 1, we don't expect to spend a lot of time in state 2 relative to state 1. We expect to see a couple of 2s and then a long run of 1s over the long haul. And that's reflected in these equalities here. And the mean time to return, the intuition is that picture over there. That's why that comes in. Okay, so now let's take the 3-minute break, and then we'll talk about the second limit theorem, which is just a stronger version of this one, as a matter of fact. Really a stronger version of this first one. So here's the second limit theorem. The second limit theorem doesn't just talk about the expected value of the fraction of the time you spend in a given state j. It talks about the actual fraction of the time you spend in state j. Okay, how does this go? In this context, so you've got a Markov chain for whatever, starting out the same way. This thing here, for every j in the state space S, nj of n divided by n converges as little n goes to infinity with probability 1. Notice that there's no e in front of this nj of n. It's just nj of n itself. The actual fraction of the time, and I'll elaborate on this a little bit in English after I'm done writing the theorem and whatever. But the point is, this converges as n goes to infinity with probability 1. Okay? Now, what does it converge to? This is kind of interesting. It turns out that, given that I start in state j, the probability, so probability sub j, that limit of, as n goes to infinity, nj of n over n equals 1 over mj is equal to 1 when j is recurrent. And here I'm absorbing both the positively recurrent and no recurrent states in the same statement, letting mj be infinity when j is no recurrent. So mj equals infinity when j is no recurrent. So this absorbs no recurrence and whatever together. And for any other state I, and if j is transient, and I'm assuming this probability sub j. No, let's absorb it into the next one. So if I is any state, then the probability, given that you start in state I, that nj of n over n converges to, so limit as n goes to infinity, nj of n over n equals 1 over mj is equal to rij when j is recurrent. And it turns out that this is one we don't really have to worry about. Finally, probability for any I, probability that you start in state I, that the limit as n goes to infinity, nj of n over n equals 0, that's equal to 1 if j is transient. All right, now this is a big mouthful of limits and probability sub this, that, and the other thing. So let me talk about it in English for a second here. Okay, so pause. This is the lecture. I'm really glad today wasn't the sick day, because that would be hard. All right, so what does this say? This says that with probability 1, every path through a set of paths of probability 1 through the Markov chain always spends a well-defined limiting fraction of the time in each of the given states. So, in English, how does this go? Every path through the Markov chain spends a well-defined limiting fraction of the time visiting any state j. Sometimes that limiting fraction of the time is going to be 0. So this limiting fraction will be 0 when j is transient or null recurrent. This limiting fraction will be, so it will be it, referring back to limiting fraction. Maybe I should write it out. Relative pronouns at a distance of 20 feet. Not good. Okay. So this limiting fraction, that's more like 27 feet. More. Yeah. Maybe if I did it in metric, I'd get it. This limiting fraction will be 1 over mj for any path that actually hits state j. Okay? Now, given that you start in state I, the probability that you hit state j is going to be rij. And that's why the limiting fraction, the probability given that you started in state I, that limit is 1 over mj is going to be rij. It's the probability that you follow a path that actually hits j. Now, the way you can visualize this you visualize as follows. The Markov chain starting in some state, so starting in any state, the chain, state I, the chain will follow a path through the state space, and provided that the state space has at least one recurrent state, so assuming that there's at least one recurrence class, what happens to this path is that sooner or later it enters some recurrent class. So sooner or later this path will be done visiting transient states and will hit, enter, whatever, some recurrence class. And once it's in that Vegas, it stays in that Vegas, right? I promised not to bring it up again, but I did. Okay? So once there, it stays there because that's a closed set. So ever after, it stays there. And so what does that mean? That means that the fraction of the time it visits any state that's not in that recurrence class that it ends up in is 0. But the limiting fraction of the time it visits all the states in that recurrence class are the 1 over mj's. So for such a path, the limiting fraction of time spent in any states outside that recurrence class is 0, and for any state j in the recurrence class, so for j in that recurrence class, the path hits j and limiting fraction 1 over mj of the time. Okay, so that's a kind of a lengthy, in English, version of the theorem about probability 1 currents. And where does probability 1 come in here? Whenever I use a word like any state I, the chain will follow a path. What I mean is, for a set of states I of probability 1, the chain will, with probability 1, follow a path, you know, blah, blah, blah. That's what I mean. Will be 0, equals 0 with probability 1. Okay, that's where with probability 1 business comes in. Drew.
The second statement that's kind of the theorem where you say if I is the statement, then the probability that it converges 1 over mj is rij. Is there a flip side to that? Is there a probability of 1 minus rij that it converges to something else? Would it be 0?
Well, see, the thing is, think of it this way. Suppose I have a recurrence class up here, Cj, and another recurrence class, Ck, right? And here's my state I, right? With probability Rij, I'm going to end up in this recurrence class. With probability Rik, I'm going to end up in that recurrence class. So the probability that this thing ends up being 1 over mj is just the probability that, given that I start in state I end up in that recurrence class. And if I have tons of other recurrence classes, each of them is going to have its own thingy. And some of them, if this is a no recurrent class, I will have 0. The probability that nj over n is equal to 0 is the probability that either every state is transient or, you know, it's always 0 when every state is transient, but if you end up in a no recurrent class.
So could you say that the probability sum I of the limit of n goes to infinity of nj of n over n equals 0 equals 1 minus rij?
No, because Rik, this could have like 1 over mk here, you know, something like that. Like, if the path ends up in this other recurrence class and it's a positively recurrent class, then the probability that then nj of n divided by n is going to converge to 1 over something else, okay? But it's not going to be 0 necessarily.
But you could
Oh, I see what you're saying. nj of n, that particular, yeah.
so it's either going to be 1 over mj or 0, right?
Yeah, it'll be that. Yeah, that's true. Yeah. Fine. I was changing the j to the k in my head, so yeah, I gave you a bad answer the first time through. All right, so these are really key theorems, and to get a even a better picture of what's going on, what we're going to need to do is talk about a different way of looking at the Markov chains, a different visualization kind of tool other than the wall of lights. And so that's what I want to talk about next time. And soon I'll be issuing absolute last call for homework 1, just so you know. And tentatively midterm Tuesday the 25th of March in class. And we'll think that through a little more to make sure there's no problems.